What if the fate of the entire universe is not fixed after all? For years, cosmologists believed dark energy was constant, a steady force pushing space apart forever. But new results from DESI now suggest something more unsettling. Dark energy may be changing with time. And if that is true, the standard model of cosmology may need a major rewrite. The future of the cosmos may not be what science once thought. If this kind of deep space mystery is worth exploring, like the video, subscribe to the channel, and stay with the story. At the widest scale that observation can reach, the universe appears as a finite visible sphere around every point that can measure it. This limit is not a wall and not an edge in the ordinary sense. It is a horizon, a boundary set by time, light, and expansion. Light travels at a finite speed, and the universe has a finite age, so only a certain portion of all existence can send any signal that arrives by the present moment. Beyond that horizon, space may continue. Observations do not show a terminating surface. They show a limit to what light has had time to cross. This visible realm is vast. It contains galaxies spread across distances so great that even light requires billions of years to pass from one region to another. Yet the horizon is not defined only by distance. It is defined by history. Every faint source at the farthest reach of observation appears not as it is now, but as it was when its light began the journey. Looking outward also means looking backward. The outermost visible regions preserve ancient conditions, and in that light the story of the universe becomes measurable. At this scale, the most important fact is simple. Space expands. Galaxies not mainly flying through a pre-existing emptiness. Instead, the fabric of distance itself changes with time. As space stretches, the light moving across it also stretches. Its wavelength grows longer. Astronomers call this redshift. A wavelength is the length of one cycle of light. At cosmic scale, greater redshift usually means greater distance and deeper time. This relation allows the expansion of the universe to be traced across long spans of cosmic history. The idea of a cosmic fate begins here, in the changing scale of space itself. If expansion slows enough, the future differs from a future in which expansion continues forever. If expansion accelerates, the difference grows larger still. For much of modern cosmology, the central task is to determine not merely that expansion occurs, but how the rate of expansion changes over time. The answer governs the long future of every large structure that remains gravitationally unbound. It governs whether distant regions become steadily harder to reach with light, whether the visible cosmos grows colder and thinner, and whether the standard description of the universe remains adequate. For many years, the working model has been the standard cosmology model, often called lambda cold dark matter. In that model, ordinary matter makes up only a small share of the cosmic total. Dark matter provides additional gravity without emitting light. Dark energy acts in the opposite direction on the largest scales, driving accelerated expansion. In its simplest form, dark energy is treated as constant in time, as though the large-scale pressure built into space does not evolve as the universe ages. This model fits a wide range of observations remarkably well. For that reason, it becomes the central framework of modern cosmology. Yet a good model remains a testable model. The horizon does not reveal its meaning all at once. It has to be measured through the pattern of distances and redshifts preserved across the sky. One of the largest efforts devoted to this task is the Dark Energy Spectroscopic Instrument, known as DESI. Its work maps millions of galaxies and quasars across a large fraction of the visible sky and across cosmic time. By measuring redshifts with high precision, DESI reconstructs how cosmic expansion behaves over billions of years. At the largest scale, it is an attempt to read the long-term behavior of the universe from the record written into light. The recent DESI results sharpen the importance of this horizon-scale view. Using its first 3 years of data, the collaboration reports stronger hints that dark energy may be evolving with time rather than remaining fixed. The result is not presented as final proof. It is described as a strengthening signal that appears when DESI data are combined with other major cosmological measurements. Observations indicate growing tension with the simplest constant dark energy picture. It remains uncertain whether this signal will persist as more data arrive and as independent analyses continue. Even so, the meaning of the result is large. If dark energy changes over time, then the standard model may require significant revision. That possibility alters the way cosmic fate is described. Under a constant dark energy picture, the far future tends toward continued accelerated expansion. Distant galaxies beyond the local gravitational neighborhood drift farther away. Space becomes darker on the largest scales as ancient light thins and redshifts. But if dark energy evolves, then the long future may depend on the form of that evolution. The acceleration may weaken, strengthen, or behave in a more complicated way than the simplest model allows. Current observations do not establish which case is real. They establish that the question remains open. At the horizon scale, the largest visible boundary is not only a limit to sight, it is also a test surface for the laws that describe the cosmos. Every improved map of distance and expansion presses on the same issue. The large-scale behavior of the universe may be governed by a constant ingredient built into space, or by something that changes as cosmic time passes. The answer determines whether the present model is stable or provisional. It determines whether the future history of expansion can be described with confidence, or only in outline. The horizon itself remains silent about whatever lies beyond observation. No measurement can describe the whole of existence directly. Cosmology, therefore, works with the observable universe, because that is the region where evidence exists. This restraint is part of the discipline. The measured sky is enough to show that the universe expands, enough to show that the expansion is accelerating, and now enough to suggest with increasing force that the acceleration may not follow the simplest fixed rule after all. The visible boundary does not close the subject. It defines the field on which the subject can be tested. So the widest region of the cosmos presents a fate that is not written once and left untouched. It appears instead as a problem under revision. The horizon keeps the outer limit in place, while light from deep time carries a record of change. Large surveys continue to compare that record against the standard model. DESI now adds weight to the possibility that dark energy evolves. Nothing in this result yet permits certainty. At the greatest scale available to observation, the universe still expands before the eye, and the terms of its ending remain unsettled. Within the wide observable realm, the next layer inward is not a single object or a single place. It is a map. The universe at great distance cannot be held in one glance, so it is assembled piece by piece, position by position, redshift by redshift, until a patterned volume begins to appear. This is the scale where the dark energy spectroscopic instrument, known as DESI, does its work. It does not search for one rare event. It builds a broad record of the large universe across much of the sky and across a long stretch of cosmic time. In that record, distance becomes structure, and structure becomes a history of expansion. A map of this kind is different from an ordinary image. An image shows a flat field of light, a deep cosmic map adds depth. Each source on the sky receives not only a direction, but also an estimate of how far away it is, based on the measured stretching of its light. The result is three-dimensional. It becomes possible to place galaxies and quasars into a vast spatial pattern rather than leave them scattered across a two-dimensional surface. This change matters because the fate of the universe is not read from brightness alone. It is read from the arrangement of matter through space, and from the way that arrangement appears at different stages of time. DESI is designed for scale. It surveys millions of galaxies and quasars, building one of the largest three-dimensional maps ever made. Each object adds one point to a much larger pattern, and no single point carries the meaning by itself. Meaning emerges only when the sample grows large enough for the underlying shape of the cosmic distribution to become clear. The map then stops looking like a catalogue and starts looking like a physical record. Dense regions, sparse regions, long arcs, and vast gaps all begin to stand out. The universe reveals itself not as a smooth mist, but as matter spread unevenly across an expanding background. This scale also introduces time in a quiet, unavoidable way. Nearby galaxies are seen in a more recent state. More distant galaxies are seen farther in the past. A deep survey therefore does not only map space, it maps the changing appearance of space across billions of years. The farther the map extends, the older the recorded layer becomes. DESI reaches deep enough to sample a large span of cosmic history, covering much of the period during which dark energy becomes important in shaping expansion. That reach is one reason its results carry such weight. The survey is not measuring only where matter sits now. It is tracing how the large-scale pattern relates to the growth and stretching of the universe over time. The size of the map is also important because cosmic structure is subtle at the larger scales. Individual galaxies have their own local histories, collisions, bursts of star formation, and internal motions. Those details matter greatly to galaxy science. But the broad expansion history is easier to read from averages across enormous numbers of objects. DESI works in that statistical way. It gathers enough sources that local irregularities begin to fade into the background. While the deeper large-scale pattern becomes more stable, the map grows quieter in one sense as it grows larger. Random detail loses power, and the underlying geometry of cosmic expansion becomes easier to test. Even the act of choosing targets reflects this large design. DESI does not observe the sky at random. It selects classes of distant objects that can mark different intervals of cosmic time. Some galaxies trace nearer eras. More luminous objects, including quasars, extend the map farther back. Together they form a layered view of the expanding universe. The map is therefore not uniform in every direction or every age, but it is broad enough to connect many parts of cosmic history into one measured structure. This continuity makes it possible to compare earlier and later epochs within the same survey framework. Seen as a whole, the DESI map is not merely large, it is deep in the literal sense of look-back time. The farther regions in the survey come from light that begins its journey billions of years ago. Those distant points belong to a younger universe, one in which the balance between matter and expansion is not identical to the balance seen today. As the map passes from nearer layers to more remote ones, it becomes a record of changing conditions. The same physical laws operate throughout, but the visible pattern reflects different stages in the long development of cosmic structure. In this way, depth becomes history written into space. From this map, cosmologists test whether the expansion of the universe follows the simplest rule expected from the standard model, or whether the record suggests something more complicated. A constant dark energy picture predicts one kind of large-scale behavior. An evolving dark energy picture can shift that behavior in small but measurable ways. DESI does not decide this by looking for a dramatic break or a sudden signal. It decides by measuring many small relations with increasing precision across the full depth of the survey. The power of the map lies in accumulation. One measured point says little. Millions begin to speak with force. This is why the recent DESI results matter in a special way. They arise not from a narrow field and not from a short-lived event, but from the gradual construction of a cosmic volume large enough to challenge a dominant model. The hint that dark energy may evolve gains meaning because it appears within this broad map of the past 11 billion years. The signal remains a hint, not a settled conclusion. Observations indicate that the case strengthens when DESI data are combined with other major measurements. It remains uncertain whether future data will preserve the same trend or reduce it. Yet the map itself changes the terms of the discussion. It places the question inside a measured history of expansion, rather than leaving it as a purely theoretical possibility. At this depth, the universe appears less like a fixed stage and more like an archive. Every distant galaxy occupies both a place and an era. Every redshift enters a larger pattern. DESI gathers those patterns into a structure wide enough to test the long behavior of cosmic expansion with unusual precision. The visible realm, once treated as a blurred immensity, becomes segmented into measured layers of time and distance. Across those layers, the present model of the universe is examined against the sky itself. The map does not announce a final verdict. It offers something quieter and more serious, a record large enough that even a small departure from expectation can no longer be ignored. When the deep map is allowed to settle into view, the large-scale pattern of the universe no longer looks random. Galaxies do not fill space in a smooth and even way. They gather into long filaments, broad walls, dense knots, and wide empty regions. This arrangement is called the cosmic web. A filament is a long thread-like concentration of matter. A wall is a flatter extended region where many filaments and galaxies appear together. Between these structures lie voids, immense regions with far fewer galaxies than average. The pattern is not decorative. It is the visible shape of gravity working over immense spans of time inside an expanding universe. At this scale, the web is the natural form taken by matter after billions of years of growth. In the early universe, matter is distributed far more evenly than it is now, though not perfectly evenly. Small differences in density already exist. Some regions contain slightly more matter than others. Under gravity, the denser regions pull in additional matter and become denser still. The less dense regions lose relative importance. Over long periods, these small early differences grow into the enormous structure seen in deep surveys. The cosmic web is therefore a record of amplification. Tiny initial unevenness becomes vast architecture. The structure develops in a universe that is expanding the whole time. That point is essential. Matter is trying to gather under gravity, while space itself is stretching. The web forms through the balance between these two tendencies. If gravity alone ruled everything at the larger scale, matter would have a greater ability to collect and condense. If expansion dominates more strongly, the growth of structure is slowed. The shape and spacing of the web therefore preserve information about how matter and expansion contend with one another across cosmic history. This is one reason DESI measures the web so carefully. A single galaxy can say little about the fate of the universe. A pattern made from millions of galaxies can say much more. The cosmic web is not read as a collection of separate objects. but as a single large system with measurable statistical properties. Astronomers examine how often galaxies appear at certain separations, how strongly they cluster, and how the pattern changes with distance and time. These measurements do not depend on one striking image or one unusual source. They depend on the regularities hidden within a vast distribution. The Webb also reveals that emptiness is part of the structure. The voids are not minor gaps between more important regions. They are one of the main components of the pattern. A void may span immense distances while containing relatively few galaxies. Its thin contents still matter, but its most obvious feature is what is missing. This absence helps define the surrounding filaments and walls. Matter drains away from lower density regions and contributes to the growth of denser ones. In that sense, the Webb is shaped by both gathering and evacuation. Structure is formed not only by matter moving into place, but also by matter leaving other places behind. The geometry of the Webb is influenced by dark matter. Ordinary matter, made of atoms, emits or absorbs light and eventually forms stars, gas clouds, and visible galaxies. Dark matter does not shine, but its gravity helps build the scaffolding on which visible structure grows. Current evidence indicates that dark matter begins shaping the large-scale distribution early, providing gravitational wells into which ordinary matter later falls. The galaxies that surveys record are therefore markers of a deeper mass distribution that is only partly visible. When DESI maps galaxy positions, it traces the luminous part of a broader structure whose full mass cannot be seen directly. This relationship between visible galaxies and underlying mass must be handled carefully. Galaxies are not perfect stand-ins for all matter. They form more readily in some environments than in others, and their local histories can be complicated, yet across a large enough survey. They still provide a powerful guide to the large-scale Webb. The irregularities of individual systems become less dominant when millions of positions are considered together. The hidden structure then emerges through collective pattern rather than direct sight. The cosmic Webb becomes legible, not because every part is visible, but because the visible parts are numerous enough to reveal the whole design statistically. Within this design, one feature is especially useful for cosmology. The Webb contains a faint preference for matter to be separated by a particular large distance scale. This feature is subtle, but it is preserved across enormous numbers of galaxies. It arises from conditions in the early universe and survives into the later arrangement of matter. DESI uses this faint regularity to measure cosmic expansion. At the level of the Webb, it appears as a slight imprint within clustering itself, a weak but persistent spacing pattern embedded in the broad structure. This is one of the key ways the map becomes a tool for testing dark energy. The cosmic Webb is therefore not simply evidence that galaxies collect. It is a measuring surface of the history of the universe. If expansion changes in one way, the observed Webb takes one statistical form. If expansion changes in another way, the pattern shifts. Because dark energy affects how quickly the universe expands and how structure grows, the Webb carries indirect evidence about whether dark energy behaves as a fixed component or as something that evolves with time. The recent DESI findings matter here because they suggest that the measured history of expansion may not fit the simplest constant dark energy picture as comfortably as once thought. The Webb does not declare this dramatically. It registers it through many precise deviations and consistencies spread across a huge volume of space. At the same time, caution remains part of the picture. The Webb is complex. Its measured form depends on observational limits, data quality, statistical treatment, and the way different traces of matter are modelled. For that reason, no single result is treated as a final answer. Observations indicate that DESI strengthens the case for possible evolution in dark energy when its measurements are considered alongside other major cosmological data. It remains uncertain whether this trend will grow clearer or weaken as more information is gathered. The Webb offers evidence, not certainty. Still, on this scale, the universe already shows something important. Its largest visible pattern is neither chaotic nor static. It is orderly in a statistical sense and dynamic in origin. Filaments, walls, knots, and voids emerge from a long contest between gravity and expansion, with dark matter shaping the hidden framework and galaxies tracing the result in light. DESI measures that structure across deep time and uses it to test the standard model against observation. In the cosmic web, the fate of the universe stops being only an abstract ending far away in time. It becomes a property written into the arrangement of matter itself, spread across the sky in silence and preserved in the largest structure that observation can map. Within the broad web, some regions gather matter with unusual force, while others remain strikingly bare. The densest regions become galaxy clusters. The emptiest become cosmic voids. These are opposite environments, but they belong to the same large design. A galaxy cluster is a vast gravitationally bound system containing many galaxies, hot gas, and a much greater mass of dark matter. A void is a region where matter is thinly spread and galaxies are comparatively scarce. Together they show the universe under two very different conditions. In one, gravity gathers. In the other, expansion has more room to express itself. Galaxy clusters are the heaviest bound structures known in the present universe. Their gravity is strong enough to hold many galaxies within a common system over immense spans of time. A cluster is not only a crowd of shining islands. Much of its ordinary matter lies between galaxies as extremely hot gas. Around and through both the galaxies and the gas lies the dominant mass component, dark matter, which cannot be seen directly but reveals itself through gravity. When all of these parts are considered together, a cluster becomes a deep reservoir of matter assembled over billions of years. The growth of a cluster is gradual. Smaller groups and individual galaxies fall inward under gravity. Gas streams into the developing well of mass and is heated by compression and motion. Dark matter helps deepen the gravitational field. Over time, what begins as a looser concentration becomes a more settled cluster. This does not produce perfect stillness. Clusters continue to evolve, and smaller systems merge into larger ones. Even so, a mature cluster stands as a region where gravity has largely overcome the general tendency of the expanding universe to separate unbound structures. This matters for the question of cosmic fate. Cosmic expansion acts most clearly on the larger scales, where matter is not held together strongly enough to resist it. Inside a cluster, local gravity dominates. The galaxies in the cluster do not simply drift apart with the stretching of space. Their mutual attraction keeps the system bound. In this way, a cluster represents a limit to the reach of expansion. It is not outside the universe's overall history, but within its own boundary, gravity is the stronger rule. Clusters show where matter has successfully resisted cosmic separation. Voids reveal the opposite side of the balance. A void is not absolute nothingness. It contains dark matter, thin gas, and some galaxies. Yet compared with the average cosmic density, it is markedly underfilled. Matter has drained away from these regions over time, pulled towards surrounding filaments, walls, and clusters. The result is a volume of space with relatively little structure inside it. In deep maps, voids can span enormous distances. They're not small gaps left between more important objects. They are one of the main ways the universe organizes emptiness. Because voids are less dense, gravity has a weaker hold there. Expansion is therefore easier to trace in these regions, at least in a relative sense. The material inside a void tends to separate more readily as the universe ages. In this way, a void can be understood as a place where large-scale expansion is less interrupted by local mass concentrations. It does not become a pure stage on which dark energy acts alone, since matter is never fully absent. Still, voids are valuable because they respond differently from dense regions. They help cosmologists see how the same cosmic laws operate across opposite environments. Clusters and voids are connected. The matter that strengthens one often comes at the expense of the other. As gravity draws mass toward dense regions, underdense regions become emptier. The contrast grows over time. Dense places tend to become denser, while sparse places lose relative importance. This shared evolution means that neither environment can be understood in isolation. A cluster is part of a surrounding network that feeds it. A void is shaped by the structures around its rim. One gathers the mass that the other lacks. These extreme regions also help reveal hidden mass. In clusters, the gravity is strong enough to bend light passing through or near the system. This effect, called gravitational lensing, allows astronomers to estimate how much total mass is present, including dark matter. The visible galaxies alone are never enough to explain the bending. In voids, the problem appears in another form. The scarcity of visible matter helps define whether mass distribution is unusually low. Together, dense and sparse regions provide complementary views of how matter is distributed through the cosmos. DESI places clusters and voids inside a much larger statistical picture. The abundance of dense regions, the size of empty ones, and the way both appear across different distances all relate to the history of cosmic growth. If gravity has more time and more leverage, structure can build efficiently, and clusters can become more numerous or more massive. If accelerated expansion suppresses growth more strongly, the formation of new large bound structures becomes harder. The population of clusters and the character of voids therefore carry information about the competition between matter and expansion. This is where the recent DESI results acquire part of their force. The survey measures the large-scale distribution of galaxies across much of cosmic history, and from that record cosmologists infer how expansion changes with time. If dark energy behaves as a fixed component, the balance between growth and expansion should follow one pattern. If dark energy evolves, that balance can shift. Clusters and voids respond in different ways, but both belong to the same test. Observations indicate that the simplest constant dark energy picture may not fit the full body of data as comfortably as before. It remains uncertain whether this signal will hold as additional DESI data are analyzed and compared with other measurements. At this scale, the universe appears divided into regions of resistance and release. Clusters are places where gravity keeps a hard-won coherence. Voids are places where matter thins, and the broad expansion of the cosmos becomes easier to read. Neither region is complete by itself. Together they define the extremes of the large-scale environment. DESI maps both as part of one connected record, using their distribution to test how the universe changes over time. In the dense heart of a cluster and in the broad silence of a void, the same question remains present. The standard model may still hold, or it may require revision. Between the dense hold of clusters and the open breadth of voids, the most familiar large inhabitants of the universe come into view. These are galaxies, great systems of stars, gas, dust, and dark matter gathered into enduring forms. In deep surveys they appear as points of measured light, but each point stands for a structure of immense scale. A galaxy may contain millions, billions, or even more stars bound together by gravity. Some are broad spirals with ordered disks. Some are rounder and more diffuse in appearance. Some are compact and active. Yet at the scale relevant to cosmic fate, their first importance is not their internal beauty. It is their use as markers placed across the expanding universe. A galaxy is large enough to persist, bright enough to be observed across vast distances, and numerous enough to reveal pattern when counted in great numbers. For this reason, galaxies serve as the main visible signposts in the deep map built by DESI. Each one occupies a position on the sky and a measurable redshift. Redshift is the stretching of light toward longer wavelengths as space expands. When the redshift of a galaxy is known, astronomers can place it within the broad history of cosmic expansion. When millions of such measurements are combined, galaxies stop being isolated systems and become a framework for tracing the changing scale of the universe. This role depends on light that reaches the observer after a very long journey. A distant galaxy is not seen in its present state. It is seen as it was when its light began to travel across expanding space. In this way, a galaxy becomes both an object and time marker. A nearer galaxy belongs to a more recent layer of cosmic history. A more distant galaxy belongs to an older one. DES uses this simple fact in a disciplined way. It measures many galaxies across many distances so that the history of expansion can be reconstructed from their collective arrangement. The recession of galaxies is one of the clearest signs that the universe expands. On average, distant galaxies appear to recede more strongly than nearby ones because the space between them and the observer has stretched by a greater amount. This does not mean that every individual galaxy moves away in a simple uniform manner. Local gravity can produce additional motions. Galaxies in a cluster orbit within the cluster. Nearby systems can move toward each other under mutual attraction. The Milky Way and the Andromeda Galaxy, for example, do not follow the broad recession pattern in the same way as distant unbound galaxies. Yet when enough galaxies are measured over large enough distances, the overall expansion becomes unmistakable. This is why galaxies are so useful in cosmology. They preserve local complexity, but in large numbers they reveal large order. A single galaxy can mislead if taken alone, since it carries its own internal motion and local environment. A population of millions smooths over these small departures and lets the broad behavior of the universe emerge. DESI relies on this statistical strength. It does not seek a perfect galaxy. It seeks a vast sample. With enough galaxies measured precisely, the expansion history can be inferred with far greater confidence than any one object could allow. Galaxies also occupy a wide range of cosmic epochs. Some of DESI's targets are relatively nearby bright galaxies. Others are more distant luminous red galaxies, selected because they remain visible over long stretches of space and time. Others are emission line galaxies, whose glowing gas makes their redshifts easier to measure even when they are farther away. Together, these populations help fill the map across much of the last 11 billion years. The survey therefore uses galaxies not only as general tracers, but as a layered population, with different kinds of galaxies helping mark different depths of cosmic history. Their measured distribution allows cosmologists to test whether the expansion of the universe changes in the way expected from the standard model. If dark energy is constant, galaxies should trace a history of distance and clustering that fits that assumption. If dark energy evolves, the relation between galaxy position, redshift, and large-scale pattern can shift in subtle ways. These shifts are small, and no individual galaxy announces them. The evidence emerges only after millions of galaxies are measured and their pattern is compared against precise cosmological models. In this sense, galaxies become the handwriting of cosmic history. Their collective spacing, not their individual appearance, carries the critical message. There is a quiet discipline in this method. A galaxy is a complicated physical system. It forms stars, absorbs gas, sheds gas, merges with neighbours, and changes shape over time. Some host active central black holes, some become relatively quiet, some continue to form new stars, while others age into redder populations. All of this matters for understanding galaxies themselves, yet DESI uses them with a narrower purpose. It asks where they are, how far away they are, and how their arrangement compares across cosmic time. The survey turns galaxies into calibrated witnesses of expansion without denying their deeper complexity. The present significance of this approach lies in what the latest DESI analyses suggest. With 3 years of data, the collaboration reports that the case has grown stronger for dark energy that may change with time rather than remain fixed. The signal is not presented as final proof, and careful uncertainty remains essential. Observations indicate that the preference for evolving dark energy becomes stronger when DESI results are combined with other major cosmological measurements. It remains uncertain whether future data will confirm this direction with greater strength or soften it. Even so, the implication is serious. The motion and distribution of galaxies across deep time may be pointing beyond the simplest version of the standard model. At the level of galaxies, the question of cosmic fate gains a visible body. These are the systems that build the map, fill the filaments, gather in clusters, and thin out toward the voids. They are the luminous inhabitants that make the expansion of the universe measurable rather than merely imaginable. Each measured redshift places one galaxy into the long outward flow of cosmic history. Each added point strengthens the map. Across millions of such points, the universe reveals not only that it expands, but that the story of its expansion may be more changeable than once assumed. In the slow recession of galaxies, spread across enormous distance and time, the future of the cosmos begins to take on measurable form. Around each visible galaxy, far beyond its bright disk or central bulge, there extends a broader and dimmer region that does not yield itself easily to ordinary sight. This is the galactic halo. It is not a sharp shell with a clean outer boundary. It is a vast surrounding domain in which dark matter dominates the mass. Thin hot gas lingers in a diffuse state, and a sparse population of old stars, globular clusters, and streams of torn material drifts through weak light. The visible galaxy occupies the center, but the halo reaches much farther. In many ways, the halo is the true outer body of the galaxy, while the shining part is only the dense inner concentration that makes the system easy to notice. The halo matters because a galaxy cannot be understood from its bright regions alone. A spiral disk full of stars may seem to define the system, yet the motions within that disk reveal something larger and more hidden. Stars and gas orbit too quickly to be explained by the gravity of visible matter by itself. The outer parts of galaxies continue to rotate at speeds that point to much more mass than light accounts for. This is one of the clearest signs that dark matter surrounds galaxies in extended halos. Dark matter does not emit light, and no direct observation yet shows its nature. Still, Its gravitational effect appears again and again in the motions of galaxies and in the larger structure of the cosmos. A galactic halo is therefore not an optional detail at the edge of a galaxy. It is the main reservoir of mass. The stars that make a galaxy beautiful occupy only a small fraction of the whole. Most of the mass lies in the unseen halo, shaping the orbits of stars, the fall of gas, and the long history of growth through mergers and accretion. Accretion is the slow gathering of matter under gravity. A galaxy draws in gas from its surroundings, captures smaller companions, and settles into a deeper gravitational well than its visible shape suggests. The halo provides that well. Without it, the galaxy would not have the same scale, stability, or structure. The stellar halo is the faintest visible part of this domain. It contains old stars spread over a large volume, often in a loose spherical distribution. Some of these stars are survivors from the early history of the galaxy. Others come from smaller galaxies that are pulled apart and absorbed over time. Their remnants can remain visible as long streams or shells, delicate traces of earlier collisions and mergers. These features show that galaxies do not grow in isolation. They assemble gradually, taking in smaller systems and incorporating their stars into the outer halo. In this way, the galactic edge becomes a record of ancient encounters. Mixed with this outer stellar population are globular clusters, dense and ancient groups of stars bound tightly together. They orbit far from the galactic center and help trace the structure of the halo. Because they are old and can be seen at large distances from the bright disk, they serve as useful markers of the galaxy's extended gravitational field. Their motions add to the evidence that the visible galaxy sits inside a far larger halo of mass. They also remind cosmologists that the outskirts of galaxies preserve older conditions than the more active inner regions, where gas, dust, and new stars often complicate the picture. The gas in the halo is different from the gas in a bright galactic disk. It is thinner, hotter, and more difficult to detect. This region is often called the circumgalactic medium, meaning the gas that surrounds a galaxy. It is not empty. It contains material flowing inward and outward over long spans of time. Some gas cools and eventually feeds future star formation in the inner galaxy. Some gas is pushed outward by stellar winds, supernova explosions, or activity near the central black hole. The halo is therefore not only a passive envelope, it is a circulation zone where matter is stored, heated, cooled, and redistributed. This circulation changes the long life of the galaxy. If gas enters the inner regions, new stars can continue to form. If gas is heated and kept from cooling, star formation can slow or stop. The halo helps regulate this balance. Its temperature, density, and motion influence whether a galaxy remains active or grows quieter with age. Even at this smaller scale, the theme of cosmic fate appears in a local form. The future of a galaxy depends not only on the stars it already contains, but also on the hidden conditions in the extended halo that surrounds it. The halo also forms the interface between a galaxy and the wider cosmic environment. Matter does not stop at the visible edge. The outer halo blends gradually into intergalactic space and into the larger web of matter that connects galaxies across the universe. Gas can arrive along filaments of the cosmic web and settle into the halo before moving inward. Small satellite galaxies can orbit within the halo for long periods before being torn apart, in a dense environment, such as a galaxy cluster. The outer halo may be disturbed by interactions with surrounding gas and neighboring systems. In a quieter region, it may retain material more gently. The halo is therefore the place where the local galaxy meets the broader cosmos. DESI does not measure galactic halos directly in the same way that it maps the positions and redshifts of millions of galaxies. Yet halos remain central to what those galaxy positions mean. Every galaxy used as a tracer in the survey sits inside a dark matter halo. The large-scale clustering of galaxies reflects, in part, the distribution of those halos through space. Galaxies form and reside within these gravitational structures, so the cosmic map that DESI builds is also an indirect map of how galactic halos occupy the expanding universe. The visible points on the survey are luminous centers of much larger invisible domains. This connection is important for cosmology. The way halos form, gather, and cluster depends on the growth of structure over time. That growth is shaped by the balance between gravity and cosmic expansion. If dark energy behaves as a constant background component, the emergence and distribution of halos follow one general pattern. If dark energy evolves with time, the pattern can shift. The differences are not read from one halo at the edge of one galaxy. They appear statistically across huge populations. Even so, the hidden halo is part of the chain that connects a single visible galaxy to the fate of the universe as a whole. At the level of the galactic halo, the edge of a galaxy becomes less definite and more revealing. Light fades, but mass continues. Stars grow sparse, yet the deeper gravitational structure remains. Thin gas circulates through a wide surrounding medium. Ancient stellar streams preserve the memory of older mergers. Globular clusters mark the far outskirts. Dark matter holds the larger form together while remaining unseen. In this quiet outer region, the galaxy shows its true scale. It is not only a bright island of stars, it is a luminous center embedded in a much larger invisible system, one whose hidden mass helps shape both the local future of the galaxy and the grander pattern that cosmology seeks to measure. Inside the broad structure of a galaxy and within the hidden reach of its halo, the next inward region is made of stars. They are the enduring visible substance of galaxies, the source of most of their steady light, and the most familiar form taken by ordinary matter on the cosmic scale. A star is a self-gravitating sphere of hot gas that shines because nuclear fusion takes place in its core. Fusion is the joining of lighter atomic nuclei into heavier ones, releasing energy as light and heat. This process gives a star its long life. But not all stars live in the same way. Their masses differ, their temperatures differ, and above all their lifetimes differ. Taken together, they form stellar populations, large assemblies of stars whose ages and properties help describe the history of a galaxy. A stellar population is not a single cluster gathered in one place. It is a broad category used to describe groups of stars that share similar ages, chemical composition, and origin. Some stars are ancient and poor in heavy elements. In astronomy, elements heavier than hydrogen and helium are often grouped together as metals. This is a technical usage, but the idea is simple. The earlier stars form when the universe contains very few heavy elements, because those elements have not yet been made in large numbers by earlier generations of stars. Later stars form from gas enriched by the remains of older stars, so they contain more of these heavier elements. By examining the light of stars, astronomers can infer some part of this history. A galaxy therefore carries not one age, but many ages at once, preserved in its stellar populations. The oldest stars in a galaxy are often found in its halo and central bulge. They belong to early periods of formation, when galaxies are assembling from smaller pieces and when the supply of heavy elements is still limited. Their light can be redder, not because they are always cooler in every case, but because old stellar populations tend to lose their hottest, shortest-lived massive stars first. These ancient stars remain as quiet witnesses of the early life of the galaxy. They are long-lived because stars with lower mass burn their fuel slowly. A small star spends energy with restraint and can survive for immense spans of time. In this sense, the oldest stellar populations become natural clocks. They do not mark time by moving hands or changing numbers, they mark it by endurance. Younger stellar populations tend to appear where star formation continues more actively. These stars can include bright blue stars with high mass and short lifetimes. Their strong light makes them easy to notice, but their brilliance is brief on cosmic timescales. A massive star burns fuel rapidly because the inward pull of gravity is stronger and the pressure and temperature in its core rise to greater extremes. The star shines more intensely, but it consumes its fuel at a faster rate. What appears most vigorous is often least durable. This contrast between slow, low-mass stars and short-lived, high-mass stars gives a galaxy much of its visible character. A quiet old galaxy glows with the accumulated light of long-lived stars. A more active galaxy can show the bright signatures of recent stellar birth. This difference also gives astronomers a way to read time from starlight. A galaxy with mostly old stars and little ongoing star formation presents one kind of spectrum and one general color. A spectrum is the spread of light by wavelength, carrying information about composition, motion, and temperature. A galaxy with many younger stars presents another. DESI measures spectra to determine redshifts with precision, but these same spectra also contain traces of stellar populations. The main goal of the survey is cosmological, not a detailed census of every star in every galaxy. Even so, the stellar content of a galaxy affects the character of its light, and therefore the way the galaxy enters the survey as a measurable source. Stellar populations also show how a galaxy changes without needing to move far through space. Stars are born, age, and die within the galaxy, so the visible balance of light shifts even when the galaxy's large-scale position remains fixed. Over long periods, active star formation can slow. Bright, short-lived stars disappear. Older and redder populations come to dominate. In this gradual way, a galaxy can age as a luminous system. It still remains a galaxy, still bound by gravity, still visible across great distances, but its inner light takes on a different character. The transformation is often slow enough that only large comparisons across many galaxies reveal the pattern clearly. At the level of stellar populations, the idea of fate becomes intimate and local. The long future of a galaxy is not only about whether it remains bound or whether distant galaxies recede beyond view. It is also about what kinds of stars continue to exist inside it. A galaxy rich in gas may continue forming new stars for a long time. A galaxy that loses or heats, that gas may become quieter, letting its existing stars age without much replacement. In either case, the population shifts steadily toward older stars as time passes and less new formation renews it. The change is not dramatic from one human lifetime to the next. It is almost entirely silent and cumulative. Chemical history deepens this picture. Early generations of stars are born from simpler material. Through fusion and stellar death, heavier elements are made and returned to space, where later stars incorporate them. As a result, younger populations often form from richer material than older ones. This means that the stars inside a galaxy preserve a record of repeated transformation. Matter does not remain in one stellar form forever. It passes through generations. The abundance of elements in a stellar population tells part of that story and places the stars within the long evolution of their galaxy. All of this unfolds beneath the larger cosmological background that DESI seeks to measure. Galaxies are used as tracers of expansion, yet the galaxies themselves are composed of stars whose populations record much slower internal histories. The redshift of a galaxy places it in the expanding universe. The stars within it place it in a biological seeming cycle of birth, maturity, and decline, though the process is purely physical and unfolds over spans beyond ordinary intuition. The local history of stars and the large history of expansion do not contradict each other. They coexist. One describes the inward life of galaxies, the other describes the outward fate of the cosmos. In the region of stellar populations, the universe appears patient. Countless stars shine at once, but they do not all belong to the same era. Some are brief flames of youth, some are durable embers that persist for ages. Together they fill galaxies with a layered light that carries memory and colour, composition, and brightness. Ancient stars preserve the early history of their systems. Younger stars show where renewal continues. DESI reads galaxies across cosmic distance, while the stars inside those galaxies reveal quieter passages of time. At this inward scale, cosmic fate is not only a matter of expansion, it is also the slow rearrangement of light itself, as stellar populations age, endure, and give a galaxy its changing inner life. Between the stars of a galaxy there lies a quieter region that is easy to overlook when attention rests on bright stellar light. This is the interstellar medium, the thin mixture of gas and dust that fills the space within a galaxy. It is not empty in the ordinary sense. It contains the raw material from which new stars can form, the remains of older stars that have shed matter back into space, and the fine grains that alter the passage of light. In this inward region, matter is no longer arranged as great systems like galaxies or as self-luminous bodies like stars. It is spread, suspended, heated, cooled, compressed, and stirred. It drifts in clouds, filaments, shells, and faint veils. Here the history of a galaxy continues in a recycled form. Most of the gas in this medium is hydrogen, with helium as the next most abundant component. Mixed into it in much smaller amounts are heavier elements made inside stars, and released through stellar winds or supernova explosions. The gas does not remain in one fixed state. Some of it is cold and dense enough to gather into molecular clouds, where atoms combine into molecules and where gravity may eventually begin to pull matter inward toward new star formation. Some of it is warmer and more diffuse, spread across larger volumes. Some of it is heated to much higher temperatures by violent events and energetic radiation. The interstellar medium is therefore not one substance, but a range of conditions through which matter passes. Dust adds another layer to this region. Cosmic dust is not soft household dust. It consists of tiny solid grains made from elements such as carbon, silicon, oxygen, and iron, often formed in the outflows of old stars or in the debris of stellar death. These grains are small, but their effect on light is large. Dust absorbs and scatters starlight, especially at shorter wavelengths. As a result, regions with much dust can appear dimmer and redder than they would otherwise look. This process is called extinction and reddening. The light has not changed at its source. It has changed during its passage through dusty space. Nebulae are the visible expression of this medium in denser or more strongly illuminated regions. A nebula is a cloud of gas and dust. Some nebulae glow because nearby stars energize the gas, causing it to emit light at specific wavelengths. Some reflect starlight and shine more softly. Some remain dark, outlined only because they block the light behind them. These clouds are not decorative features placed between stars. They are active environments in which matter is stored, transformed, and sometimes prepared for the next generation of stars. They carry the chemical products of earlier stellar lives and redistribute them through the galaxy. The interstellar medium is always moving, though often slowly. Shock waves from exploding stars compress nearby gas. Radiation from hot stars pushes on surrounding material. Galactic rotation shears clouds and stretches them into filaments. Gravity draws the densest regions inward. At the same time, turbulence stirs the gas on many scales. Turbulence means irregular, chaotic motion rather than smooth flow. In a cloud of gas, it can help support the cloud against collapse for a time, while also creating pockets of greater density where collapse later becomes possible. In this way, the medium remains dynamic even when it appears calm from far away. This drifting matter also preserves the chemical memory of earlier generations of stars. Hydrogen and helium dominate because they are the basic ingredients left from the early universe. But heavier elements accumulate through repeated cycles of stellar birth and death. A star forms from gas, fuses lighter elements into heavier ones, and later returns some of that enriched matter to space. The next cloud then begins from a richer mixture than the one before. Dust grains incorporate some of these heavier elements, and molecules assemble in colder, denser regions. The interstellar medium becomes the place where a galaxy stores the products of its own past and prepares them for reuse. Light passing through this medium carries evidence of these conditions. When astronomers spread light into a spectrum, they can detect dark absorption lines or bright emission lines that reveal the presence of specific elements and physical states. A spectrum is light separated by wavelength so that its detailed structure can be measured. Each chemical element leaves a characteristic pattern. Gas that is glowing produces emission features. Gas in front of a bright source can absorb certain wavelengths and leave absorption features. Dust changes the overall shape and color of the spectrum by dimming and reddening the light. In this inward region, matter speaks through its effect on light. This is one reason spectra are so important to DESI. The survey does not merely image galaxies as points on the sky, it measures their spectra with great precision. From the shift of known spectral features toward longer wavelengths, astronomers determine redshift and place each galaxy within cosmic history. The method depends on the fact that gas in galaxies and around active sources produces recognizable lines, while stellar populations contribute a broader background of light, even when the primary goal is cosmology. The path to that goal runs through the interstellar medium and the way it shapes the light entering the instrument. The gas and dust inside galaxies help make the cosmic map measurable. Emission line galaxies are especially useful in this regard. Their gas glows strongly at specific wavelengths, often because young stars or other energetic processes excite the surrounding material. These sharp features make redshift easier to measure, especially for distant galaxies. In other galaxies, absorption features from stars and gas provide the needed pattern. The point is not that every cloud is studied in full detail by DESI. The point is that the survey depends on the physical truth that matter between and around stars leaves a readable structure in light. Without gas, dust, and spectra, much of the map would lose its precision. At the level of cosmic fate, this region seems local and modest, yet it remains connected to the wider problem. DESI tests the expansion history of the universe through redshifts measured from light. That light has to pass through the interior material of galaxies, emerge with detectable spectral structure, and reach the observer after a journey through expanding space. The faint hint that dark energy may evolve with time depends in part on careful measurements extracted from these spectral signatures. Observations indicate that the current standard picture may be under pressure, but the pressure is read from details carried in light. Gas and dust do not decide the fate of the universe by themselves. They help reveal it by marking the light with physical information that survives the long passage outward. In the interstellar medium, a galaxy appears less like a collection of finished stars and more like a circulating system of matter. Gas cools, warms, gathers, and disperses. Dust dims and reddens starlight while preserving the products of older stars. Nebulae glow, reflect, or darken the regions they occupy. Spectra gather all of this into evidence. The space between stars is not a pause between more important objects. It is a working interior where matter is stored in transit, and where light acquires the signatures that astronomy can read. At this inward scale, the changing fate of the universe remains present in a quiet form, carried not by dramatic motion, but by the subtle lines and altered colours that drifting gas and dust leave upon light. At the level of gas, dust, and spectra, light carries the marks that instruments can measure. Deeper within the logic of the map, another layer appears. It is not a place that can be visited and not an object that can be isolated in the sky. It is a pattern hidden inside the distribution of galaxies themselves. This pattern is the standard ruler used by DESI to trace the expansion of the universe. A standard ruler is a feature whose true physical size is known, so that its apparent size at different distances can reveal how space has stretched over time. In modern cosmology, the most important large standard ruler comes from baryon acoustic oscillations. Baryons are the ordinary particles that make up atoms, and acoustic oscillations are pressure waves moving through a fluid. The phrase sounds technical, but the basic idea is simple. In the early universe, matter and radiation once moved together in a hot, dense medium, and waves travel through it. When conditions change, the waves stop. But their characteristic scale remains imprinted in the later arrangement of matter. This preserved scale is subtle. It does not appear as a neat ring around every galaxy, or as a line that can be drawn across the sky. Instead, it emerges statistically when enormous numbers of galaxies are measured together. There is a slight preference for galaxies to be separated by a particular large distance scale. The preference is weak, but it is real. And because the underlying physical scale is known from early universe physics, astronomers can use it as a ruler laid across cosmic time. DESI is built in large part to measure this ruler with exceptional precision. The origin of the ruler lies in a much earlier state of the universe, when ordinary matter is not yet arranged into stars or galaxies. The young cosmos is hot, dense, and filled with a mixture of charged particles and light. Because light scatters from charged particles, radiation and matter are tightly coupled. Regions that are slightly denser than average feel the inward pull of gravity, but the intense radiation pressure pushes outward. The result is a wave pattern, a repeated inward and outward response moving through the hot plasma. These are the acoustic oscillations. They're called acoustic because they resemble sound waves in the sense that pressure drives them through a medium, though the medium is not air and no ordinary sound is involved. As the universe expands and cools, a turning point arrives. Electrons combine with nuclei to form neutral atoms, and light is no longer trapped in the same way. The radiation decouples from matter and begins to travel freely through space. At that moment, the pressure-driven waves can no longer continue in their earlier form. The outward-moving shells in the ordinary matter stop advancing, and the preferred scale reached by that time becomes fixed into the distribution of matter. Later, as gravity builds galaxies and the cosmic web, this old scale remains as a faint statistical imprint. It is weak because billions of years of structure growth complicate the pattern, but it is not erased. The importance of this standard ruler is that it links very early physical conditions to the later geometry of the expanding universe. If the true size of the ruler is known, then measuring how large it appears at different redshifts reveals how cosmic distances behave. A ruler seen in a more expanded universe can appear differently than the same ruler seen in a less expanded one. In this way, cosmologists use the preserved scale to reconstruct the history of expansion. The method does not rely on guessing the intrinsic brightness of individual objects. It relies on measuring a collective spacing pattern in the large-scale distribution of galaxies. DESI applies this method across an enormous three-dimensional map. It measures the redshifts of millions of galaxies and quasars, then searches statistically for the slight excess of pairs separated by the characteristic scale of baryon acoustic oscillations. The signal is not dramatic to the eye. It becomes visible only through careful counting and precise analysis. This is why the survey needs such vast numbers. The preferred separation is a small effect buried inside the complexity of cosmic structure. Only a very large sample allows the ruler to emerge clearly enough for precision cosmology. The ruler can be measured in more than one direction. Across the sky, it helps determine how the apparent transverse scale changes with distance. Along the line of sight, it helps determine how redshift intervals correspond to physical distance. These two aspects together give cosmologists a way to test the expansion history in detail. They can estimate how the scale factor of the universe changes and how the expansion rate behaves at different cosmic times. In simple terms, the ruler helps answer not only whether the universe expands, but how that expansion proceeds across billions of years. This makes baryon acoustic oscillations especially valuable for the question of dark energy. A constant dark energy picture predicts one specific pattern for how cosmic distances evolve. If dark energy changes with time, the inferred expansion history can shift. The baryon acoustic oscillation ruler is one of the cleanest available tools for detecting such shifts because it is anchored in well-understood early universe physics and then measured later in the large-scale galaxy distribution. It acts as a bridge between early conditions and late-time geometry. DESI relies on that bridge. The recent DESI findings gain much of their force from this method. With its first 3 years of data, the survey measures the baryon acoustic oscillation scale across a long span of cosmic time with increasing precision. When those measurements are compared with the simplest standard cosmology model, the fit remains broadly strong, yet signs of strain begin to appear. Observations indicate that the picture may align better if dark energy is allowed to evolve rather than remain strictly constant. This does not amount to a final overthrow of the standard model. It remains uncertain whether the preference will strengthen, weaken, or change form as more data are added. Even so, the standard ruler has become sharp enough that small mismatches now matter. There is calm severity to this result. The ruler itself comes from a very old process, set long before stars, galaxies, and clusters take their present shapes. It survives not as a visible monument but as a slight statistical leaning in the spacing of matter. DESI measures that leaning across much of the observable sky and much of the last 11 billion years. The method is quiet, cumulative, and resistant to spectacle. Yet it carries exceptional weight because it lets the geometry of the universe be tested against a preserved physical scale. When that test begins to suggest that the present model may be too simple, the implication reaches far beyond one dataset. At the level of the standard ruler, the universe appears as a place that retains memory in pattern. Ancient waves leave no direct roar behind them, only a spacing that persists through the later growth of structure. Galaxies gather into webs and clusters. Yet beneath that complexity, the old scale remains. DESI reads it with enough precision to make the fate of the cosmos into a measurable question. If the ruler continues to indicate that dark energy evolves, then the long expansion history of the universe may have to be described in new terms. For now, the ruler remains what it has always been in cosmology, a quiet, fixed measure held against a changing universe. At this inward stage of the story, the great structures of the universe begin to serve a narrower purpose. Galaxies, clusters, voids, halos, stars, gas, and the preserved standard ruler all become parts of one larger measurement. That measurement is the expansion history of the universe through time. Expansion is not a single event completed in the distant past. It is an ongoing change in the scale of space. The scientific task is to determine how fast that change proceeds at different eras, and whether the rate follows the simplest pattern expected from the standard cosmology model. Time enters the problem through light. A nearby galaxy is seen in a more recent state. A distant galaxy is seen as it was much earlier. When redshifts are measured across a wide range of distances, the sky becomes a record of many ages observed at once. DESI uses this principle on a large scale. Its map spans much of the last 11 billion years, so the survey can compare the geometry of the universe at many stages rather than infer the whole history from only a few epochs. The value of this method lies in accumulation. One distance measurement can only hint at the behavior of expansion. Many measurements spread across deep time can reveal whether the rate changes smoothly, whether it accelerates, and whether the acceleration behaves in the way the standard model predicts. Cosmologists therefore seek not only precision at one redshift, but a sequence of precise measurements across many redshifts. A redshift is the amount by which light is stretched by cosmic expansion. Because redshift usually increases with distance and look-back time, it functions as a marker of cosmic era. DESI turns millions of such markers into a timeline built from observation rather than assumption. The broad outline of that timeline is already well established. The universe expands from an earlier, denser state. For billions of years after the first stages of cosmic history, matter plays a dominant role in shaping the expansion rate. Gravity acts to slow the outward growth of scale. Later, dark energy becomes increasingly important on the larger scales, and the expansion begins to accelerate. This transition is one of the central discoveries of modern cosmology. The standard model describes it successfully in broad terms by treating dark energy as a constant component of the cosmic energy budget. DESI now tests that picture with greater detail. Using the standard ruler preserved in baryon acoustic oscillations, the survey measures cosmic distances at different redshifts and reconstructs how expansion behaves across time. The ruler has a known physical scale inherited from the early universe. By seeing how that scale appears in different eras, cosmologists infer how much space has stretched between those eras and the present. Together, the measurements form a curve, a history of distance against redshift, from which the character of expansion can be read. If dark energy is constant, this history should follow a specific smooth relation. Small observational errors are expected, but the overall pattern should remain stable. If dark energy evolves with time, the relation can bend away from that simple expectation. Instead, it can appear as a mismatch spread across many redshifts, small at any one point but harder to ignore when the full history is viewed together. This is the kind of tension DESI begins to expose. The importance of the recent DESI result lies partly in its tone. The collaboration does not describe the evidence as decisive proof that dark energy changes. It describes a strengthening preference for models in which dark energy evolves, especially when the DESI measurements are combined with other major cosmological datasets. Observations indicate that the expansion history inferred from current data may fit better when dark energy is allowed to change with time. It remains uncertain whether that preference will strengthen into a more robust conclusion as additional DESI data are gathered and analysed. Even in this uncertain state, the effect on cosmology is serious. Expansion through time is one of the central quantities from which the large-scale behaviour of the universe is inferred. If the measured history departs systematically from the expectation of constant dark energy, then the standard model may be missing part of the physical description of the late universe. Dark energy itself may evolve, or some related assumption in the model may need adjustment. This does not erase what is already known. The universe still expands. The expansion is still accelerating. The broad success of the standard model remains real. DESI does not overturn these foundations. It presses on the finer structure of the timeline. It asks whether the acceleration follows the same strength at all later epochs, or whether its influence shifts as the universe ages. This is a more demanding question than the earlier discovery of acceleration itself. There is also a deeper reason this region of the subject feels unsettling. Expansion through time links present observation to future fate. If the past history of expansion is not quite what the simplest model predicts, then projections of the far future become less secure. A constant dark energy picture leads to one long-term path of continuing acceleration. An evolving dark energy picture can alter that path, even if only gradually. At the level of measurement, this means that the timeline of the universe is the physical basis on which later cosmic destiny is inferred. Yet the evidence remains quiet. Nothing in the sky shifts visibly from night to night. The change appears only in the disciplined comparison of measured distances, redshifts, and models. DESI reads the expansion history in that patient way. It gathers millions of points, extracts a faint ruler from their spacing, and lays that ruler against the history of the universe. The result is not spectacle. It is a gradual sharpening of doubt directed at one of the simplest assumptions in modern cosmology. In the region of expansion through time, the universe becomes a measured sequence of eras connected by changing scale. The deep map turns into a timeline. Redshift becomes age. Distance becomes history. DESI follows that history across billions of years and finds that the late expansion of the cosmos may not be governed by a perfectly constant dark energy after all. The signal remains provisional, and caution remains necessary. Even so, the measured curve of cosmic expansion now carries a new weight. It suggests that the fate of the universe may depend on a quantity that does not sit still, but changes slowly with time as the cosmos itself grows older. When the expansion history has been measured as carefully as possible, the next inward region is not a place in space, but a framework of interpretation. Cosmologists do not stop at the map, the ruler, or the timeline. They ask what set of ingredients can reproduce the observed pattern most faithfully. This framework is the standard cosmology model, the compact description that links the large-scale expansion of the universe to its main contents and to the geometry of space in this region. The subject becomes less about visible structures themselves and more about the parameters that describe them in the simplest coherent form. The standard model assumes that the universe, when viewed on the largest scales, is remarkably uniform. This does not mean that galaxies clusters and voids vanish. It means that when enough volume is averaged together, the cosmos can be described by broad quantities rather than by every local irregularity. The most important of these quantities are the amount of ordinary matter, the amount of dark matter, the contribution of dark energy, and the curvature of space. Curvature means the large-scale geometric shape of space itself. A flat geometry follows the ordinary rules of Euclidean space on the larger scales. A positively curved geometry bends back on itself in a way loosely analogous to a sphere. A negatively curved geometry opens outward in the opposite sense. Observations over many years indicate that the large-scale geometry is very close to flat. Matter enters the model in two distinct forms. Ordinary matter includes atoms, stars, gas, dust, planets, and every familiar physical substance. Dark matter adds gravity without producing light in the ordinary way. On cosmic scales, ordinary matter is the smaller share. Dark matter supplies much of the mass that shapes structure formation and galaxy motion. Dark energy enters differently. It is not inferred as an extra attractive mass. It is introduced because the large-scale expansion of the universe accelerates, and this acceleration requires a component with very different behavior from matter. In the simplest version of the model, dark energy remains constant in time. This set of ingredients has great power because it is spare. With relatively few parameters, the model describes a wide range of observations, the large-scale distribution of galaxies, the growth of structure, the expansion history, and the relic patterns left from early cosmic conditions. Such success is not trivial. A model survives in cosmology because it fits different kinds of evidence at once. The standard picture earns its authority through repeated agreement with observation, not through simplicity alone. Yet the same compactness that gives it elegance also makes it vulnerable. If one part of the observed universe begins to resist the fit, the strain can spread through the whole framework. This is the region in which DESI now exerts pressure. The survey measures the expansion history with increasing precision, especially through the standard ruler encoded in baryon acoustic oscillations. Those measurements do not sit by themselves. They are interpreted inside the standard model. Cosmologists ask which combination of matter density, dark energy behavior, and curvature best reproduces the measured distances across redshift. If the simplest assumption of constant dark energy is sufficient, the fit should remain stable as the data improve. If the data steadily prefer a different behavior, then the model may still function broadly while showing localized strain in its parameters. A fit in cosmology is not a matter of visual preference. It is a disciplined comparison between predicted patterns and measured ones. A chosen set of parameters generates an expected expansion history and a related structure history. Those expectations are then tested against the data. If the mismatch remains small and statistically ordinary, the model is retained. If the mismatch becomes systematic and increasingly difficult to dismiss, the model may need revision. This does not always mean that the whole framework collapses. Sometimes one parameter shifts. Sometimes an additional degree of freedom is introduced. Sometimes a previously fixed quantity is allowed to vary. The present DESI discussion lies within this careful territory. One of the central tests concerns whether dark energy must remain fixed in time. In the standard picture, it does. This assumption produces a specific relation between the amounts of matter, the near flatness of space, and the late-time expansion history. DESI now suggests that the measured history may fit better if dark energy is allowed to evolve. The evidence is not yet final, and the collaboration presents it with restraint. Observations indicate a growing preference for a time-varying dark energy description when DESI results are combined with other major cosmological measurements. It remains uncertain whether this preference will strengthen into a robust conclusion or diminish as more data are gathered. Curvature is part of this fitting problem because it can sometimes imitate the effect of other ingredients if the data are limited or imprecise. A small deviation from flatness can alter inferred distances. So can a change in matter density. So can an evolving dark energy component. Cosmologists, therefore, do not treat these parameters in isolation. They are adjusted together and tested as a linked system. A successful model is one in which the same parameter values explain many different observations at once. This is why the question raised by DESI is serious. If the best fit begins to pull away from the simplest model, the tension is not confined to one number. It touches the internal balance of the entire framework. There is a quiet discipline in this stage of the subject. Nothing dramatic appears in the sky. The pressure accumulates inside tables of likelihoods, model comparisons, parameter ranges, and statistical consistency tests. Yet behind this technical surface lies a simple physical issue. The universe expands in a certain way. Matter gathers in a certain way. Space appears to have a certain geometry. A good cosmological model must make these behaviors belong together. If one ingredient has been described too simply, the data eventually begin to show it. For now, the standard model still stands. Its broad achievements remain substantial. Ordinary matter, dark energy, and near-flat geometry still provide the best compact description of the observable universe. DESI does not erase that success. It exposes a possible weakness in the assumption that dark energy is perfectly constant. That weakness matters because constant dark energy is not a minor decorative feature of the model. It is one of its central stabilizing assumptions about the late universe. In this inward region of matter, curvature, and fit, cosmology becomes an exercise in balance. Too much matter changes the pace of expansion and the growth of structure. Too little matter leaves the observed universe underbound. A meaningful curvature shifts the geometry of distance. A constant dark energy drives one late-time history. An evolving dark energy drives another. DESI places new weight on the possibility that the balance may need to be adjusted. The model still holds the cosmos together in a coherent form, but it no longer appears entirely at rest. Within its fitted parameters, a small unease has begun to grow. Far deeper than galaxies, clusters, and the measured spread of structure, there remains a much older layer of evidence that reaches the present as light. This is the cosmic microwave background, the faint afterglow of the early universe. It fills all directions of the sky with nearly uniform radiation, and for modern cosmology, it serves as one of the most important records ever observed. The light does not come from stars or galaxies. It comes from a time long before either exists in their later form. In this region of the subject, the universe is examined not through its present structures alone, but through ancient radiation that preserves the conditions from which those structures later grow. The cosmic microwave background begins when the universe is young, hot, and dense enough that light cannot travel freely for any significant distance. Ordinary matter exists as a plasma, a state in which electrons and atomic nuclei move separately, rather than remaining bound into neutral atoms. In this state, light scatters repeatedly and the universe is opaque. As expansion continues, the cosmos cools. Electrons eventually combine with nuclei, and neutral atoms form in large numbers. Once this happens, light interacts much less strongly with matter and begins to stream through space with far greater freedom. The radiation released from that era continues to travel across the universe and reaches the present in a vastly stretched and cooled form. What remains remarkable is not only that this light survives, but that it carries structure. The cosmic microwave background is nearly uniform, yet not perfectly so. Tiny temperature variations appear across the sky. These minute differences reflect slight differences in density and conditions in the early universe. Regions that are a little denser than average later help seed the formation of galaxies and the larger cosmic web. In this way, the background preserves a record of the early pattern from which later structure develops. It is not a photograph in an ordinary sense, but it is a map of ancient conditions written in radiation. This makes the cosmic microwave background an essential cross-check for every later measurement of the universe. DESI studies the expansion history and large-scale structure across much of the last 11 billion years. The microwave background comes from a far earlier epoch and encodes the initial conditions against which later cosmic evolution is tested. If the standard model is correct in its simplest form, then the early signal preserved in the background and the later signal measured in galaxy surveys should fit into one coherent description. The same basic ingredients should connect them: the amount of matter, the shape of space, and the large-scale behavior of dark energy should be mutually consistent. The background also helps anchor the standard ruler used by DESI. The characteristic scale preserved in baryon acoustic oscillations begins in the early plasma that the microwave background records. In the background, this ancient physics appears as a pattern in the temperature fluctuations across the sky. In the later galaxy distribution, it appears as a faint preferred separation scale between galaxies. These are not separate stories. They are two views of the same underlying early process, seen first in ancient light and later in the mature arrangement of matter. This connection gives the ruler its unusual strength. Its physical origin is checked by one dataset and its late-time appearance by another. Because of this, the cosmic microwave background acts as a test of coherence. It does not simply provide an early measurement that can be admired on its own. It has to agree with what later surveys see if the same cosmological model is to remain trustworthy. The early universe inferred from the microwave background leads to predictions about how structure should grow, how distances should behave, and how expansion should proceed. DESI then measures those later outcomes directly. If both line up cleanly, confidence in the model rises. If they begin to pull against each other in subtle ways, the model may require adjustment. This is part of the meaning of the present DESI result. The survey does not operate in isolation. Its measurements are compared with the microwave background and with other major observations that trace the later universe. When this combined comparison is made, this simplest constant dark energy picture appears less secure than before. Observations indicate that the fit can improve when dark energy is allowed to evolve with time. The signal remains tentative rather than final. It remains uncertain whether the tension will strengthen as data accumulate or whether improved analysis will reduce it. Even so, the cross-check from ancient light is what makes the issue especially serious. A late-time discrepancy matters more when it is measured against an early signal of such precision. The microwave background is valuable partly because it is physically simple compared with the later universe. Later cosmic history includes galaxies with complicated internal processes, gas flows, star formation, black hole activity, and many overlapping environments. The early radiation comes from a cosmos that is, in some respects, easier to model on large scales. Its small fluctuations can be described with great precision. For that reason, it provides a clean starting point. When late-time surveys disagree with the simplest extrapolation from that starting point, cosmologists pay close attention. Other cross-checks also contribute to this picture. Supernova measurements help trace the late expansion history through standardizable brightness. Weak gravitational lensing traces how matter bends light, and therefore how structure grows. Galaxy clustering beyond the standard ruler adds more information about the distribution of matter. None of these stands entirely alone. Each has its own uncertainties and modeling challenges, yet together with the cosmic microwave background and DESI, they form an interlocking set of tests. The strength of modern cosmology lies in this overlap. A conclusion becomes persuasive when many methods converge. At present, the convergence remains broad but not perfectly still. The standard cosmology model continues to explain a great deal. The cosmic microwave background remains one of its strongest supports. DESI does not cancel that support. Instead, it presses on how the early and late universe connect. The ancient light suggests a beginning of the story described with extraordinary precision. The later map of galaxies now hints that the ending of that story may not follow the simplest path once assumed. This does not break the framework outright. It introduces a measured strain between the elegance of the early description and the growing detail of the late one. In the region of ancient light, the universe appears as a preserved memory. The sky carries radiation from a time before stars, before galaxies, before the cosmic web takes its visible form. Tiny fluctuations in that light record the early seeds of everything that follows. DESI measures the later expansion of the cosmos and compares it against this old pattern. The comparison is exacting, because it links the first readable conditions of the universe to the long history that comes after. At this inward scale, cosmic fate is checked against cosmic origin. Ancient light remains in place across the whole sky, calm and nearly uniform, while the measurements drawn from it continue to test whether the present model still holds without revision. Beneath the visible architecture of the universe and beneath the ancient light that records its early state, there remains a deeper layer that cannot be seen directly at all. It is known only through effect. Dark matter and dark energy belong to this hidden region. They do not present themselves as bright objects or glowing clouds. They are inferred from the way gravity shapes motion, from the way structure forms, and from the way cosmic expansion changes with time. In modern cosmology, these unseen components dominate the large-scale story. Ordinary matter, the material of stars, planets, gas, dust, and living bodies, is the smaller share. The greater part lies in forms that remain physically obscure. Dark matter is the older of the two great hidden problems in the sense that its role becomes clear first in the growth of structure. Galaxies rotate too quickly at large radii to be held together by visible matter alone. Galaxy clusters contain too much gravity to be explained by their stars and hot gas. Gravitational lensing, the bending of light by mass, reveals more matter than telescopes can see. Large-scale simulations of cosmic structure match observation much better when this additional invisible matter is included. Across many lines of evidence, dark matter behaves as a form of mass that gathers under gravity and helps build the scaffolding of the cosmic web. Yet dark matter remains dark in more than name. Its composition is unknown. It is not simply ordinary matter hidden in faint objects, because the total amount and behavior required by cosmology do not fit that explanation. It does not emit light in the way atoms do. It does not appear to collide strongly with itself or with ordinary matter except through gravity, at least not in any way that has yet been clearly observed. For cosmology, this means dark matter can be described by its effects even while its deeper nature remains unsettled. It acts as the hidden mass that allows galaxies, halos, clusters, and the web itself to form as observed. Dark energy is different in nearly every important way. It does not help matter gather. It enters the cosmic story through the late-time acceleration of expansion. When astronomers discovered that the expansion of the universe is speeding up rather than slowing down under gravity alone, the standard model required an additional component with very different large-scale behavior. This component is called dark energy. The name marks ignorance rather than explanation. It describes an effect that appears to drive accelerated expansion, but it does not identify a known substance in the ordinary sense. In the simplest cosmological picture, dark energy is treated as a constant property of space itself. This idea is mathematically compact and has long fit a broad range of data very well. In that description, the large-scale pressure associated with dark energy remains fixed, while matter thins out as the universe expands. Over time, dark energy becomes increasingly dominant because matter is diluted by expansion, whereas the constant dark energy term does not fade in the same way. This leads naturally to a late universe in which acceleration continues and distant unbound galaxies recede ever farther away. For many years, this constant picture has served as the working foundation of late-time cosmology. It is economical, successful, and deeply embedded in the standard model. Yet success in science does not remove the obligation to test. As measurements grow sharper, the hidden sector of the universe comes under greater pressure. The question is no longer only whether dark energy exists in some effective sense. The question is whether its influence remains truly constant over cosmic time or whether that influence changes slowly as the universe ages. This is the point at which DESI becomes central. By mapping millions of galaxies and quasars, and by tracing the expansion history over much of the past 11 billion years, DESI measures the late-time behavior of the cosmos with exceptional precision. The survey does not detect dark energy directly. No instrument sees dark energy as an object. Instead, DESI infers its effect through the geometry of distance, the standard ruler preserved in baryon acoustic oscillations, and the changing rate of expansion across redshift. In this way, the hidden component is tested through its imprint on the visible arrangement of matter. The recent DESI results sharpen this hidden problem. The collaboration reports that with 3 years of data, the evidence grows stronger for a picture in which dark energy may evolve with time rather than remain perfectly constant. The result is presented carefully. It is not a declaration of final proof. Observations indicate that the preference becomes more notable when DESI data are combined with other major cosmological measurements. It remains uncertain whether the signal will strengthen further, remain at a suggestive level, or weaken as more observations and analyses accumulate. Even so, the meaning is substantial. One of the central assumptions of the standard cosmology model may be too simple. The specific tendency discussed in connection with DESI is not toward a stronger and stronger dominance of dark energy, without limit in the simplest sense often imagined in popular accounts. Instead, the current signal points more toward the possibility that dark energy's influence may be weakening over time relative to the constant case. This remains a model-dependent inference rather than an established fact. What matters most at present is that the data may prefer change over perfect constancy. If that preference survives, cosmology will need a broader description of the late universe than the present standard form provides. Dark matter and dark energy therefore occupy different roles within the same hidden region. Dark matter shapes structure by adding gravity and helping matter collect. Dark energy shapes fate by affecting how the scale of space evolves at late times. One helps build galaxies and clusters. The other influences the long outward flow that separates unbound regions of the cosmos. Both are invisible in the ordinary sense. Both are known through consequence. Yet only dark energy, as DESI now suggests, may be showing signs that its role changes with time in a way that directly challenges the simplest current model. This hidden region is unsettling not because it is chaotic, but because it is so dominant and so poorly understood. Most of the cosmic budget lies in components that do not glow. The visible universe, rich with stars and galaxies, is only a minor luminous fraction of the whole. Cosmology can measure the effects of the hidden majority with growing precision, yet the physical identity of that majority remains uncertain. DESI adds a further layer of unease by suggesting that one of these invisible components may not even be constant in the way the most successful model assumes. In the realm of hidden cosmic components, the universe appears stable in outline and unfinished in explanation. Dark matter continues to hold structure together across many scales. Dark energy continues to drive accelerated expansion. Those broad statements remain intact. What changes is the degree of confidence attached to their simplest description. The unseen is no longer only obscure in composition. It may also be variable in behavior, at this inward depth. The fate of the universe rests on influences that cannot be touched or directly seen, only inferred from the patient motion of galaxies, the preserved ruler of ancient waves, and the quiet curvature of the cosmic timeline itself. At this depth of the subject, the hidden components of the universe begin to turn into possible endings. The question is no longer only what dark energy is called or how it is measured. The question becomes what kind of future follows from its behavior. Cosmic fate is not a separate story added for dramatic effect. It is the long result of the same expansion history that DESI measures across the observable sky. Once the expansion of the universe is known to be accelerating, the far future changes. Once there is reason to suspect that the driver of that acceleration may evolve with time, the future becomes less fixed than the standard picture assumes. The simplest fate follows from constant dark energy. In that case, the large-scale expansion continues to accelerate in a steady general way. Galaxies that are not gravitationally bound to one another recede ever farther apart. Over immense spans of time, distant systems slip beyond practical communication and then beyond visibility, as the light they emit becomes increasingly stretched and faint. Local bound structures remain coherent for much longer. Galaxies already tied together by gravity do not simply dissolve because of the large-scale expansion. Yet outside these bound islands, the wider universe grows emptier in appearance. The night sky, viewed from any surviving local system in the far future, would contain less and less of the larger cosmos. This constant dark energy future is often described as a long thinning of the observable universe. Stars continue to age and die within galaxies. Gas available for new star formation gradually declines. The great web of large-scale structure no longer gathers unbound regions together, because accelerated expansion increasingly suppresses that possibility. In the broadest sense, the cosmos trends toward isolation, dilution, and thermal decline. This is sometimes called heat death, not because everything becomes hot, but because usable energy becomes harder to concentrate into the differences needed for active processes. The universe approaches a state that is more uniform, colder on large scales, and less able to sustain the kinds of structure that flourish earlier in cosmic history. If dark energy evolves, this clean picture becomes less certain. The future then depends on the direction and form of the change. If the influence of dark energy weakens over time relative to the constant case, the acceleration may soften. The universe would still be expanding, and it may still expand forever, but the long-term rate of separation would differ. Structure growth in the later cosmos might be suppressed less strongly than in the constant case. Though by the present era the largest bound structures are already largely established. The crucial point is that weakening dark energy changes the pace and character of the far future, even if it does not reverse expansion outright. A different theoretical possibility appears if dark energy strengthens with time. In that case, acceleration could become more severe than in the standard model. The most extreme versions of this class of behavior lead to a future in which the expansion rate grows so dominant that progressively smaller gravitationally bound systems are threatened. In the most violent form of the idea, sometimes called a big rip, even galaxies, stars, planets, and eventually smaller structures could no longer remain intact. This is a mathematically explored outcome rather than an observationally established expectation. Current measurements do not require it, and the recent DESI hint does not point most naturally in that direction. It remains one possible fate within the wider family of evolving dark energy models, not the preferred reading of present evidence. There is also the long-standing possibility of a future recollapse, in which cosmic expansion eventually halts and reverses. In older cosmological discussions, this is associated with a universe whose self-gravity ultimately overcomes outward motion. Under the present broad observational picture, this does not appear to be the favoured outcome. The observed acceleration of expansion works against it, and current data strongly support a late universe in which dark energy plays a substantial role. Still, if the hidden physics behind dark energy were more complex than the standard model allows, some more intricate long-term behavior cannot be excluded in principle. Observations do not presently indicate that recollapse is the leading expectation. This is what makes the DESI result so consequential without making it conclusive. The survey does not reveal a dramatic new ending directly. It shows that the late-time expansion history may fit better if dark energy is allowed to change over time. The difference is subtle at present, but subtlety is enough. Cosmic fate depends on cumulative behavior carried over immense durations. A small change in the rule governing late expansion can produce a significantly different remote future. Not through sudden rupture, but through steady divergence over time. The future of the universe is sensitive to the long persistence of its governing terms. In the current state of evidence, one outcome remains firm. The universe is expanding, and the expansion is accelerating in the present era. Beyond that, certainty weakens. If dark energy remains constant, the standard picture of endless accelerated expansion remains the best simple description. If dark energy weakens, the far future may be less relentlessly isolating than that model predicts, though still expansive and increasingly diffuse. If dark energy strengthens, more extreme futures become possible, though current observations do not favour the most violent versions. What matters most is that the future is tied to empirical measurement, rather than to free invention. It is not chosen from imagination. It is constrained by the geometry of the observed universe. This has a quiet effect on the idea of cosmic destiny. Fate, in this scientific sense, is not an assigned purpose. It is the long-term consequence of physical conditions acting on the larger scales. The term carries emotional weight in ordinary language, but in cosmology it means the outcome implied by expansion, matter, geometry, and the behavior of dark energy, DESI, sharpens that meaning by suggesting that one of the key terms may not be fixed after all. The result does not replace one clear ending with another. It replaces confidence with a more measured uncertainty. Even this uncertainty has structure. Not all futures are equally plausible. Constant dark energy remains a strong and successful baseline. Evolving dark energy is a growing possibility, not a settled fact. Theories that predict violent disruption of bound systems exist, but current evidence does not place them at the center of expectation. More modest departures from the standard future are easier to accommodate within the present data. The future therefore appears neither fully stable nor fully unbound to evidence. It sits inside a narrowing range of possibilities, some calmer than others, all governed by the same hidden physics now under renewed scrutiny. In the region of cosmic fate itself, the universe appears as a long consequence still being measured. The great map of galaxies, the preserved standard ruler, the ancient microwave background, and the fitted model all lead here. They converge on the future not by prophecy, but by extension of the observed past and present. DESI now suggests that the rule of acceleration may be more changeable than the standard cosmology model assumes. That suggestion is enough to make the far future less settled. The ending of the universe remains governed by law, but the exact form of that law may still be shifting beneath the surface of the visible sky. At the deepest inward point of the subject, the visible universe, the hidden components, the measured ruler, the ancient background light, and the projected future all narrow into one final region. It is the boundary of present explanation. Here the issue is not a galaxy, a cluster, a void, or even dark energy by itself. The issue is whether the standard cosmology model remains complete enough to carry the weight placed upon it. A scientific model does not fail because it is imperfect in every detail. It fails when improved observation begins to reveal that one of its central assumptions no longer holds the evidence together without strain. This standard model still describes the large-scale universe with extraordinary success. It accounts for the broad pattern of expansion, the growth of cosmic structure, the near-flat geometry of space, and the relic light of the early cosmos with a compact set of ingredients. This achievement remains real. It is the reason the model becomes standard in the first place. Yet in science, a successful model is not protected from revision by its past strength. Its continued value depends on whether new measurements continue to fit within its simplest form. Precision is what turns quiet unease into a serious problem. DESI brings cosmology into that precise territory. By measuring the expansion history across much of the last 11 billion years, it tests not only whether the universe accelerates, but whether the late-time rule of that acceleration remains as simple as the standard model assumes. The recent signal suggesting that dark energy may evolve does not erase the model's major successes. It does something more subtle and more important. It begins to separate broad correctness from final completeness. A model can still be right in outline while becoming incomplete in a crucial term. This is often how science changes at the highest level. A framework may continue to describe most of what is observed, while a small but persistent mismatch gathers at one edge. The mismatch is first treated cautiously, because complex measurements can produce temporary tensions. Instruments improve, methods are revised, and independent groups test the same claim in different ways. If the signal fades, the model regains calm. If the signal grows, the model is not always discarded entirely. More often it is expanded, generalized, or replaced by a broader description that preserves its earlier successes while explaining the new discrepancy. Cosmology stands near that threshold now, though it has not crossed it conclusively. The present strain lies in the late universe. Observations indicate that the simplest picture of constant dark energy may not fit as comfortably as it once did when DESI data are combined with other major cosmological measurements. It remains uncertain whether this trend will harden into a compelling case for evolving dark energy. The uncertainty matters, and scientific restraint remains necessary. Yet even in uncertainty, the implications are large. Constant dark energy is not a minor convenience inside the standard model. It is the term that stabilizes the late expansion history and supports the familiar prediction of a steadily accelerating cosmos. If that term changes, the whole late time interpretation must be reconsidered. This reconsideration would reach beyond one parameter. If dark energy evolves, cosmologists must ask whether the change reflects a new field, a new aspect of gravity on large scales, an interaction within the hidden sector, or some other extension not captured by the present model. Observations do not yet identify which explanation, if any, is correct. They indicate only that the constant description may be too narrow. This is the deepest kind of scientific discomfort. The data may be revealing not a numerical correction alone, but a missing part of the physical picture. At this boundary, ignorance becomes sharply defined. Cosmologists know that most of the universe is not described by visible matter. They know that dark matter behaves gravitationally in a way that helps build structure. They know that dark energy, whatever its deeper nature, is tied to accelerated expansion. They know that the standard model provides a powerful working account of these facts. What they do not yet know is whether the hidden sector obeys the simplest fixed rules currently assigned to it. DESI presses directly on that uncertainty. It does not remove the darkness from dark energy. It deepens the suspicion that its behavior may be more complex than the existing model allows. There is no disgrace in this limit. A model under pressure is not a failure of science. It is one of the signs that observation is becoming strong enough to reach beneath an earlier layer of understanding. The history of physics proceeds in this way. An old framework remains useful until new evidence demands a wider one. The older picture is often retained as an approximation within the newer structure. In that sense, the present cosmological moment is not one of collapse. It is one of tension between a remarkably successful baseline and a set of increasingly precise measurements that may be starting to exceed it. This boundary also has an emotional character, though the science itself remains neutral. The universe appears legible on vast scales. It offers a standard ruler from ancient waves, a background light from the early plasma, a web of matter spread across billions of light years, and a measurable history of expansion. These are immense accomplishments of observation and theory. Yet at the core of the interpretation, the fate of the cosmos may depend on a component whose physical identity remains unknown, and whose strength may not even be constant. The more clearly the universe is measured, the more sharply this unfinished center comes into focus. For now, the deepest honest statement remains simple. The standard cosmology model continues to work very well. DESI has not overthrown it. The evidence for evolving dark energy is suggestive and strengthening, not final. The case matters because it touches the future of cosmic expansion and the adequacy of the dominant model at once. If the signal persists, cosmology will likely enter a period of substantial revision, If it fades, the current model will stand more firmly than before. Having survived a serious test, either outcome is scientifically valuable. At the innermost boundary of present knowledge, the universe appears neither solved nor unknowable. It appears measured to a remarkable degree and still incomplete at its core. The sky yields distances, histories, structures, and relic light with extraordinary discipline. DESI adds to that discipline by making the late-time expansion of the cosmos more precise than before. In doing so, it raises the possibility that the standard model may require a major change in one of its most important assumptions. The fate of the universe remains tied to that unresolved point. The deepest mystery is no longer whether the cosmos can be studied. It is whether its most successful modern description has begun, quietly and measurably, to reach the edge of its own sufficiency. The measured universe now grows quiet. The larger structures remain in place across the mind as patterns of distance, light, and time. The horizon holds its limit. Galaxies continue their slow recession. Ancient radiation still crosses space from a much earlier state. Hidden mass still shapes the web. Dark energy still enters the equations of the late cosmos, whether constant or changing. Nothing in this picture rushes. Everything unfolds over spans so long that motion becomes almost indistinguishable from stillness. Within that stillness, the deepest uncertainty remains gentle rather than chaotic. Observations have become precise enough to show that the standard description of the universe may not be complete in its simplest late-time form. That possibility does not erase what has been learned. It adds a softer edge to certainty. The cosmos remains lawful, measurable, and coherent. It also remains unfinished in explanation. Its fate is not a tale waiting to be told in dramatic terms. It is a physical consequence, slowly emerging from light, structure, and expansion. The stars inside galaxies continue their long aging. Gas and dust continue their quiet circulation. Bound systems hold together where gravity is strong enough. Far beyond them, space continues to widen. The future depends on how that widening changes, and whether the unseen pressure behind it stays fixed or slowly evolves. For now, the answer remains incomplete, held between strong evidence and remaining doubt, so the universe rests as a vast measured mystery. It is neither fully known nor beyond understanding. It offers enough to trace its history, enough to test its models, and enough to show that even its broadest fate may still be under revision. The sky remains calm while the evidence deepens. The outer darkness keeps its distance. The inner questions remain open. Across all scales, the cosmos continues in silence, steady and immense, carrying its final outcome forward through time,